We start with a simple traveling sine wave. Inside a laser, light is reflected between two mirrors. Traveling sine waves move in opposite directions. The constructive and destructive interference of these two waves creates standing waves. Standing waves have stationary nodes. What will happen if a standing wave is made up of two traveling waves having slightly different frequencies? Waves are formed on the standing waves. These are called modulation envelopes. They move. However, the zero crossing points, the nodes, do not move. Now we look at standing waves inside a laser. Traveling waves bounce back and forth between two mirrors, forming standing waves. If we move this laser at 5% of the speed of light, the two traveling waves become Doppler shifted. Modulation envelopes are created. With no motion, the uniform standing waves return. We will now use these same concepts to create a wave-based model of an electron. To achieve the correct de Broglie wave properties, the wavelength of the standing waves in the electron model must equal an electron's Compton wavelength. If an electron's standing waves equal an electron's Compton wavelength,
then the modulation envelope matches an electron's de Broglie wavelength and velocity.
the question then becomes, are spherical standing waves capable of producing the required de Broglie wave properties? To answer that question, we will now simulate spherical standing waves. Expanding hemispherical shells are used to represent spherical traveling waves. This is a cross-section representation of spherical traveling waves. Outward propagating spherical traveling waves. And now we see an example of them moving inward. When these two traveling wave patterns are present simultaneously, standing waves are formed. This again is the result of constructive and destructive interference. We have been viewing the prior examples in a stationary frame of reference. Now we will look at these same examples in motion. We start with outward propagating standing waves. When these traveling waves are moved at 25% the speed of light, these Doppler effects appear. With no motion, the undistorted traveling waves return. Inward traveling waves exhibit a different Doppler distortion. Inverse Doppler shift distortions occur. And now we superimpose these two Doppler shifted wave patterns. Linear modulation envelopes are created on the spherical standing waves. The previous example presumes the standing waves are in a moving frame of reference. The foregoing simulation and mathematical analysis implies it is possible to simulate an electron's de Broglie properties in spherical standing waves having an electron's Compton frequency. Such a rotating wave has a specific frame of reference. It therefore acquires all the same properties of confined light in a laser. The article discusses the means by which rotating waves achieve this necessary fixed frame of reference. The closest analogy for this electron model is a quantum vortex. These are soliton waves that have been created in a superfluid. They spin without friction. They are fundamentally waves but possess particle properties. Now we have enough information to proceed with an overview description of the proposed electron model. Shown here is a representation of the core of an electron. It is a wave in the universal field rotating at about 10 to the 20th hertz. This wave has an undetectable amplitude of Planck length. Even though the core is rotating at the speed of light, it possesses a specific frame of reference. This is another way of representing the distortion of the universal field produced by the rotating wave in the electron's core. This wave, which has Planck length amplitude, has no detectable volume. Therefore, it appears to be a point particle. This type of rotating distortion will produce outward radiating traveling waves, which take the form of an expanding Archimedean spiral. The article postulates the universal field has resonances in which a wave reflects its own wavelengths. In particular, the electron's Compton frequency is such a resonance. Therefore, an electron's outward traveling waves reflect their own wavelength and create inward propagating traveling waves. So when we superimpose the inward and outward spiral traveling waves, an interference pattern is created. The presence of both inward and outward traveling waves creates standing waves. These rotating standing waves take on special properties. For example, the nodes form concentric circles and do not move. However, the entire pattern rotates. Shown here is a two-dimensional representation of an electron's standing wave structure. It possesses the same fundamental standing wave properties that we looked at earlier. To see these shared properties, we need to examine a cross-section view of the electron's standing waves. The standing wave cloud produces distortions in the universal field. The amplitude of these distortions decreases with distance, but the distortions extend indefinitely. These external standing waves generate an electron's gravitational and electric fields. The primary distortion is a linear effect that scales with amplitude. It creates an electron's electric field. The second-order distortion is a nonlinear effect that scales with amplitude squared. This is what creates an electron's gravitational field. Here, a second electron's core is shown immersed in the rotating standing waves of the first electron. The second electron encounters a distorted universal field. The primary distortion creates the electrostatic force on the second electron. The much weaker nonlinear distortion creates the gravitational force felt by the second electron. This model predicts these two forces have a single source and are intimately connected. The accompanying paper explains in much more detail how the wave-based electron model physically generates both of these forces.